Hello, students. This is Halverson, Professor Halverson, Dr. Halverson, whatever. Um, I want to pick up the notes where we left off last time. And uh, one thing I want to do before I get into the new stuff is I just want to show you a little bit here about pressure. Um, I've got here the simulation going, and you could see that it's got a pressure gauge. And look at what happens to the pressure when I go up. Notice that the pressure, which is right now the absolute pressure, it's reading 101 kilopascals. That's roughly 1 atmosphere of pressure. But as we go down, there's a little bit more air pressure. That's because there's a little bit more air above the gauge. And then when you get into the water here, the pressure climbs very quickly. And that makes sense because now you have the water above the gauge as well as the atmosphere. And as you might guess, if I add more water, make the water level go up, look at that, the pressure goes up. And if I let the water level down, the pressure goes down. So yeah, this thing reads at absolute pressure. Now I'm going to put this away and let's get into the notes. So here are the notes. Okay, so we left off just this is where we left off last time, and this is where I'm going to begin this time. I'm on page 6 of the notes, where we're talking about buoyancy. So buoyancy is what holds a boat up in the ocean. And it's what makes it kind of hard to swim down to the bottom of the swimming pool because the water is sort of, your body wants to float. And so why is it that there's such a thing as buoyancy? Well, as you saw in the simulation just a few seconds ago, the deeper the gauge is in the water, the higher the pressure. So, so if you have some object in the water, here I've got some three-dimensional object, well, the pressure, and let's see if I can get this thing going. Watch what happens. I'm going to turn on my highlighter. Yeah, okay, you see that? That's my highlighter. So the pressure at the top of the object, which is here, is a little bit higher than the pressure at the bottom of the object, which is right there. So in order to make this easier to explain, I'm going to make this be a really simple object. It's like a beer can, an empty can, and it's in the water. It's filled with air. Okay, so I've got this can, and the pressure on the top of the can, which is pushing down, is less than the pressure on the bottom of the can, and the pressure at the bottom is pushing up. So basically what that means is the upward force is going to be less than the downward force. All right, so let's do some math here. The pressure at the top of the can, which is this, is the density of the water times the depth times gravity, 9.8. So, okay, that's the pressure at the top of the can. The pressure at the bottom of the can, which is over here, is going to be the density of water times the depth plus the extra depth, which the height of the can gives you a little extra depth, and that quantity times gravity. So the upward force, which is the pressure times, well, actually, this is going to be the downward force, which is the pressure times the area, is going to be the density times the depth times the area of the can times g. And the force on the bottom of the can, which is the upward force, will be the density plus d plus a times e plus h plus times the area times gravity. Okay, the net force, right, which is going to be what we want, the net force is going to be the force at the top plus the force at the bottom. And the force on the top is downward, so it's negative. The force on the bottom is upward, so it's positive. You take the difference of these two things. Let's clear this. And you get that the force is given by this. Let's turn this on again. This is the force on the overall can. So it's rho times h times the area of the bottom of the can times g. But if you think about the geometry of this, the volume of the can is the area of the top or bottom times its height. Woohoo! So that means that the net force is equal to the density times the volume of the can times gravity. Now, I just did it for a can, but this is going to work for any shape. And here, let's clear this. It works for any shape, and so the general rule is that it's the density of the water or the fluid, could be any fluid, times the volume of the object that's in the fluid times gravity. And so there you go. That is the rule of buoyancy. And it's got a special name. This thing is called Archimedes' principle. There it is. Okay, now that you've seen the basic math, let's get into a couple of examples. So I'm on the next page now. Let's consider two things that are in the water. On the left, I have an underwater float, and on the right, a boat. We'll start with the underwater float. So this float is underwater, and it's being held down by the tension of a rope, and the rope is anchored to the bottom of the ocean. Now, we're going to think of this float as a hollow sphere. It has a radius r of 0.4 meters, and its mass, the stuff that the shell, the construction of the float has a mass of 120 kilograms. So the question is, what is the tension in the anchor line, in the rope that is holding the float down? So we start by doing a free body diagram. And so here we go. We've got, let's turn the highlight on here. We've got, this represents, oh, all right, here we go. This this dot here in the middle is the float itself, and the downward vector is the longer one is the downward pull of the rope, and in addition to that, we have the weight of the shell of the float itself, the weight of the 120 kilograms. Then the upward vector is the buoyancy. So the tension is going to be given by the buoyancy force, but minus the weight, because the weight is helping hold the float down. So first, according to Archimedes, the buoyancy force is going to be the density of the water, uh, which is rho, times the volume of water times gravity. So it's basically the weight of the volume that's been displaced by the float, the volume of water that's been pushed aside by the float. And so, okay, we've got the density here, and I put here the formula for a sphere. The volume of a sphere is 4/3 pi r cubed. That's this right here. So there's your volume. And okay, so rho times the volume is the mass, and then the mass times gravity gives you the weight. So now that we've got the different pieces, we put it together. So here is the tension, which is going to be equal to the buoyancy. Here's the buoyancy minus the weight. I'm plugging in the numbers here. This is for the buoyancy, and now the numbers for the weight. And we get altogether 1,517 newtons, and it's a downward pull, but I didn't. Let's see. Why don't I have a negative sign here? Okay, well, I had to stop and think about it for a little while, and I realized that there's a little mistake in these notes. So just backing up a little bit, we know we have an equilibrium situation. We know that because the float is not moving. So that means that the net force on the float, let's see here, the net force on the float is going to be equal to 0. Now, that means that each of the forces acting, when you add them all up, you're going to get 0. So let's look at each force. So the first one I have here is the buoyancy force. The second one is its weight, and the third one is the tension in the rope. So this formula, 0 equals F sub B plus the weight plus the tension. Let's solve that for the tension. And so, okay, I'm going to subtract F sub B and W from both sides, and I'm going to have the tension equal to minus the buoyancy force minus the weight. But the thing is that this weight is downward already, and so this weight here is actually going to be minus m times g. Okay, so what then that means is that everything is sort of gets turned around. Over here is going to become minus, and minus times minus becomes plus. And so here I need a negative sign, here I need a plus sign, here I need a negative sign, here I need a plus sign, and here I need a negative sign. And yes, now it makes sense. It's downward. Okay, so I think we've taken care of the float example. Okay, now let's look at the next example. It's the rectangular boat, which I have floating on top of the water. Let's scroll down to the explanation for it. Okay, so this rectangular boat has a mass of 25 tons, or 25,000 kilograms. And the question is, how far below the surface will it float? In other words, how deep will the bottom of the boat be? So what's this distance right here going to be? Okay, so when we're thinking about this, we maybe start by thinking about the boat before it gets in the water. It's above the water, and you ease the boat. It touches the surface and it starts to go into the water, and as it goes down, the buoyancy increases, and at some point, the buoyancy will equal the mass of the boat. And so when that happens, the boat is floating and the net force is zero because the boat doesn't go down in the water anymore, it doesn't go up, just the water is holding up the boat nice and steady. So now the net force, which is equal to zero, is given by the buoyancy force, which is holding it up, minus its minus mg, the weight. And yeah, uh, so so we're going to have here we've got zero is the buoyancy force, rho vg minus mg. We're going to solve for v, and there's got a few steps in this process, but the first step is going to be to solve for v. So let's see, we can divide everything by g, right? We have g in common, so we divide everything by g, so we're left with rho v minus m equals 0. Then we're going to add m on both sides, and then we're going to divide by rho. And so you wind up with v equals m times rho. But okay, so now the next step is to remember that that the volume v is given by the depth of the boat, how deep it sinks, and the area of the boat, looking down on it. That's why I made it a rectangular boat. It's to make the geometry simple. So the depth that it sinks to times the area will equal the mass over rho. And now I'm going to solve for the depth, which is what we wanted. And so depth is equal to the mass of the boat divided by the area times rho. We plug in the numbers. The boat's mass was 25 tons. And the area of the boat, which is 3 meters by 10 meters long. And then we multiply by the density of seawater. Seawater is a little bit more dense than fresh water. Yeah, actually, come to think of that, I should have mentioned that this density here of 1,025 kilograms per cubic meter, that played a role in the float example as well. So yeah, we've got that in the end, the boat sinks to a depth of 0.813 meters. Since we just talked about the ocean seawater being more dense, it's interesting to see that if that same boat were to go from ocean water, which has a density of 1,025 kilograms per cubic meter, if it were to go to fresh water, like a lake, where the density is much closer to 1,000, then this denominator here is going to be smaller, and so the result is that the boat will sink a little bit deeper into the fresh water than it does when it's out on the ocean. Okay, so that's it for Archimedes' principle.